So these are a couple of glow-in-the-dark stars with the light on, which is exciting the electrons. And as those excited electrons drop down to a non-excited state, it releases energy. And that energy comes off in the form of an electromagnetic wave or photon. And the frequency of that is going to tell us what is going to dictate what color that is. And so if the light's back on, then it's charging back up. So when you're looking at something that glows in the dark, you get that to glow by having it underneath the light for a good amount of time. And so what happens when you put it underneath the light, you send in with white light, you have a lot of different frequencies. And so that particular atom you're going to excite some electrons based on one of those frequencies. White light has a whole bunch, so it doesn't matter. And so there will be electrons jumping up to higher levels while that's happening. And so when you're adding light, you are making the electrons jump up and they become excited. They're in the excited state. Then when you take the light away and you turn it off and it's dark out, those stars will glow. What happens is these electrons that are in the excited state drop back down to a lower state and they're more stable. In that situation, it's going to give off some energy in the form of an electromagnetic wave, which is a photon. And depending on what energy is being given off, will help us identify how much, depending on what wavelength is giving off, will help us to identify how much energy is given off. And every atom has a particular pattern of energies that will be given off as different levels are shifted. And so not only can you figure out how much energy is given off, you can also use that information to figure out what atom you actually have. So this is what it can look like for hydrogen, and it has the various levels, and the amount of energy that is released is figured out by the change in those levels. And so there's lots of different combinations that you can have here. You can have from this one, from the n equals 5 down to n equals 4. This will give you the change in the amount of energy released. You can have it drop from 5 to 3, you can have it drop from 5 to 2, and you can have it drop from 5 to 1. And it does this in a single jump. If it drops and rests in one spot, then that is the amount of energy that's given. It doesn't swirl down, it just drops 1, 2, 3 each time. You can go from here, from 4 to 3, you can go from 4 to 2, and you can go from 4 to 1. You can go from 3 to 2, you can go from 3 to 1, and you can go from 2 to 1. And so these are all the different combinations that could be found as that electron is dropping from an excited state down to a more stable state. And depending on what that shift is going to show us the amount of energy that's released in there. That amount of energy released corresponds with a certain wavelength of light. And so by using that, we can make some different calculations. We have this equation for Planck's constant. We have E, the energy, is equal to H, which is Planck's constant, times the frequency. And so H is actually Planck's constant. And that's equal to 6.63 times 10 to the negative 34th joules times seconds. Frequency is the frequency of the wave. Remember, it's within an electromagnetic spectrum, and so if you need to find the wavelength, you can use C to do that. So this is the frequency of the wave, and that'll be measured in hertz, and then you have your energy released. And this will be calculated in joules. Usually you'll see it in electron volts. And so that's why I have this up here, that 1 electron volt is equal to 1.60 times 10 to the negative 19th joules. And so any combination of different things will help you to figure out either your frequency or your energy. And so let's take a look at what we have here. We have this drop, and let's say we're going from 4 to 3. So we're taking the drop from 4 down to 3. So we'll look at the difference in the values here. So we'll take 1.51 minus the 0.85. You're looking at the difference here. And when you do that, you get 0.66 electron volts released. And in this situation, because we're going from a higher level to a lower level, it lets us know that we're releasing that energy in the form of the electromagnetic wave. If the arrows are being drawn up, it means that you're adding energy and you're making the electron go into the excited state. So if we're looking from, it's falling from 4 down to 3. So we'll find the difference here. We have 0.66 electron volts. We need to get those electron volts into joules in order to work with the equation that we have. And so we'll take 0.66 electron volts times 1.60 times 10 to the negative 19th joules per electron volt. And when we do that, we end up with 1.056 times 10 to the negative 19th joules. So in this drop, as this is being dropped, this electron's going from level 4 down to level 3. It releases 0.66 electron volts, which is equal to this many joules. Now we can put that into the equation that we have for Planck's constant. So now we can say that E is equal to HF. And if we're looking for the frequency, we'll rearrange that to be that frequency equals E over H. So we can take this energy that we have, 1.056 times 10 to the negative 19th joules, divided by Planck's constant of 6.63 times 10 to the negative 34th joules times seconds. So joules will cancel out. You'll have 1 over seconds left as your unit. 1 over seconds gives us our hertz, which measures frequencies. When you calculate this out, you end up with your frequency here is 1.59 times 10 to the 14th hertz. This can also correspond with a wavelength, because you know that C equals F lambda. So lambda equals the speed of light in a vacuum over the frequency. And so we can say 3 times 10 to the 8th meters per second over the frequency of 1.59 times 10 to the 14th hertz. And when you do that, you end up with 1890, or it's 1.89 times 10 to the negative 5th meters. And then you can get that into nanometers, 1890 nanometers. So with this falling, it'll fall outside of the electromagnetic spectrum. It's a longer wavelength, so it falls in the infrared part of that spectrum. So that's one way of looking at it. If we look at a different drop, let's say we go from 3 down to 2. That was getting really small. So let's say we're going from the 3rd level down to the 2nd level. And so the numbers that we have for that, we'll have 3.40 minus 1.51, and that's going to give us 1.89 electron volts. To get that into joules, we'll take the 1.89 electron volts times 1.60 times 10 to the negative 19th joules per electron volts. And what we end up with here is 3.024 times 10 to the negative 19th joules. So that's the amount of energy in joules that's being released as that electron drops from the 3rd level down to the 2nd level. Remember, it's being released as a photon. Sorry, I think I said electron, photon. So as your photon takes off, it has this energy with it, and that energy corresponds to a wave. And so we'll take and say, well, we know that E equals HF, so F equals our energy over Planck's constant. And so we have 3.024 times 10 to the negative 19th joules, and then divided by 6.63 times 10 to the negative 34th joules times seconds. When we take and divide this out, again, the joules cancel out. You have 1 over seconds. That gives us hertz, which is good because frequency is measured in hertz. And then we end up with 4.56 times 10 to the 14th hertz. We can get that into our wavelength. Sometimes you need to, sometimes you don't. But if we were to take and figure out where that falls in the electromagnetic spectrum, we could take C equals F lambda. So we would say our wavelength is equal to C over F. So 3 times 10 to the 8th meters per second over their frequency of 4.56, so super high frequency, times 10 to the 14th hertz. And that ends up giving us 6.58 times 10 to the negative 6th meters. To get that into nanometers, we would have 658 times 10, or sorry, we would say that as 658 nanometers. So with 658 nanometers, we know that we have a red line that's happening here. So what we're looking at is this, this is times 10 to the negative 7th. Sorry, I put that wrong. 10 to the negative 7th, 658 nanometers, and we have a red line here. So what we can do then is we can take and see if we can work in the other way. If we don't know the energy that's being released, but we know the amount of, we know the wavelength that's of the light that's being emitted, or of that electromagnetic wave, then we could go and figure out what energy is being released. In the data book, you'll see two equations. The first equation is the one that we've been talking about, the E equals h, or Planck's constant times the frequency. The other one is that the wavelength is equal to h times c over e. And so these both can go back and forth like I did before. I took the frequency and then was able to calculate the wavelength. You can just stick them in here all in one shot if you like. If you take the idea of C, or the equation of C equals F lambda, and rearrange that for F, you have F equals C over lambda. And so if you take and put that in there, you have E equals H. Instead of having F, you have C over lambda. And so that gets close to this. We need to bring the lambda to the other sides. We multiply both sides by lambda, cancel that out, and then divide by E. Cancel that out, and then that gives us the lambda equals our Planck's constant times the speed of light over the energy that we have. And so there's no preference on which way you do it, but both of these equations will show up in the data book for you to see.